Another way in which mixture models give you flexibility for modeling data is when dealing with zero-inflated data. In zero-inflated data, what you get is a larger number of zeros than you would expect under one of your standard models. We're going to consider here two examples. One is zero-inflated counts. Zero-inflated counts may arise, for example, in the study of biological data. When you look at your data, you may see that you have a large number of counts that are reported as zeros, and that may not be very well explained by any standard probability model, such as the negative binomial or the Poisson model. So let's see here one example of how we can create a zero-inflated version of the negative binomial distribution. In this example, I'm going to plot probability mass functions for values of x between 0 and 15. And I'm going to create, in this first example, two different graphs. One that corresponds to a negative binomial or to data that follows a negative binomial distribution with parameters 8 and 0.6. So this means that the probability of success is 0.6 and that then the Bernoulli trials stop after 8 successes. And we can easily do that. That's going to be the first graph in a panel of two graphs. And we know that this is how the negative binomial distribution looks like. In general, by changing the parameter 8 and 0.6, you can get a wide range of shapes for the negative binomial distribution. But in all the cases, what you may be doing is essentially stretching and condensing this particular unimodal shape that you can see here. So if you reduce the probability of success, for example, you may start shrinking the peak towards the left until a point where what you see is just a decreasing distribution. But in every case, the distribution will be unimodal that you generate from this. That may not be very good in practice because what we may see in real life is, for example, a large number of zero counts. So a first peak here, a mode here, and then we may see a second mode somewhere further down the road. One example of this arises in biology when you consider the number of nests when you do bird counts that contain no eggs versus the number of eggs that are present in nests that do have eggs. You typically have a peak here that corresponds to birds that couldn't mate or that didn't generate any eggs. And then you have a full distribution for the number of eggs in other nests that typically doesn't just fall directly from zero, so it's a small and then has a second peak up here. So there are a number of practical applications in which you want to allow the distribution to have those two peaks, one at zero and one somewhere away from zero. One way to do that is to combine one of the standard distributions like the negative binomial or the Poisson with a point mass at zero with some additional weight associated with the zero probability down here. And that is just a mixture model of two very special types of distributions. One that is a point mass that puts all probability in a single location, and a second one that has a range of values that is wider than just a single value. And graphically, we can get that by essentially combining. In this case, we're giving 20% probability to point mass at location 0. And we are giving 80% probability, 1 minus 0.8, to the negative binomial distribution that we just saw that is being plotted here. So this is how we compute the probability mass function for that mixture of a point mass and the negative binomial distribution. And we can add it to the plot very easily. And now what we have here in the lower panel is that mixture of the same distribution that you have up here with a point mass at 20. And you can see that now the probability of having 0 counts is 0.2, which is what the weight associated with the point mass, plus this little bit of probability here about 0.2 that is given by the negative binomial distribution to the count 0. And what you get for all the other values is essentially the same numbers that you were getting here, but now multiplied by 0.8. So that when you add up all the values, you still get a total probability of 1 over all values of the random variable. A second example of a mixture distribution that is useful for dealing with zero-inflated data is the case where you want to mix a point mass with a continuous distribution. This often happens when you study time to events. Sometimes the time to events are 0. Imagine that you are studying the lifetime of, for example, a light bulb that you buy in the supermarket. For most light bulbs, that's going to be a very long time, but some of them come defective from the factory and they never work. So for those items, the lifetime is 0. So you want to be able to combine a continuous distribution, for example, a log-normal distribution, a Weibull distribution, an exponential distribution, with a discrete point mass at 0 that captures those components that are defective from the manufacturer. So the way to do that is, again, to use a mixture model that involves both a point mass at 0 as one of the components and a second component that models the lifetime of the components that are not defective. As before, we're going to do a little example. We're going to plot the density of this mixture distribution, in this case over the range -2 to 15. This is a distribution that is going to have support only on the positive numbers. So the plot at starting at -2 is just to illustrate how the point mass affects the distribution, but the density for negative numbers will be 0, as we will see in a second. We're going to, again, try to contrast what happens if we don't put in the point mass and what happens if we put in the point mass as one component of the mixture. So first we're going to just plot the density of the log-normal distribution over this range of values of x that we just discussed. And the parameters of that log-normal distribution are going to be 1.5 and 0.5. So if you remember, the log-normal distribution is the distribution, or it's the distribution of a number whose logarithm follows a normal distribution with, in this case, mean 1.5 and standard deviation 0.5. So this is kind of our reference or our baseline for comparison. And in addition to that, we're going to consider the mixture of that same density with a point mass at 0. And in this example, I'm going to give the point mass at 0.3. In my example that I discussed before, this means that I expect about 30% of my components to be defective. So when you go to the supermarket to buy the light bulb, about 30% of the light bulbs come defective from the factory. And then the rest, the other 70%, is going to have a lifetime that follows this reference distribution that I discussed before. And in this case, I'm going to plot both of them in the same graph. And we can see here how the shapes change. So for negative values, both densities are 0, which means that we don't allow negative values. That makes a lot of sense. We cannot have negative lifetimes for the light bulbs. The main difference happens down here. I should note that these are the cumulative distribution functions. These are not the densities, unlike in all the previous examples that we had considered. And the reason why we moved to work with the cumulative distribution function rather than the density is to be able to clearly illustrate the effect of the point mass at 0. So again, coming back here, the difference is what happens at 0, whereas the regular log Gaussian distribution starts at 0 and starts just increasing smoothly until it reaches 1. In the case of the mixture of the point mass and the log Gaussian distribution, the cumulative distribution function has a jump at 0. That is where the point mass that we mixed in is located. And it jumps exactly to 0.3, which is the value of the way that we gave the point mass. And then starting from there, it essentially takes the same shape as the log Gaussian density. It's just that it has been moved up or wrapped up so that, or scaled up, so that this beginning point matches the point up here, the 0.3, where the point mass ends. So this allows us to capture this probability that an item is defective and therefore doesn't last any time, all the way to the component lasting as long as it may last.